Hello, everyone. Thank you for joining us today for this webinar on selecting the right data warehouse. My name is Parag, and I work as a product marketing manager at Hevo. I'll be your today's host and moderator for this webinar. Let me introduce you to our today's speaker, Gaurav Bahrani, who is a VP engineering at Hevo. So before we start our today's session, I would like to remind you of a few things. All attendees will be on listen only mode. We are going to record this webinar and we'll be sharing with you the recording post this session. You can type in your questions anytime during the webinar in the Q&A window available on your screen, and we will address them one by one at the end of the session. Okay, so before we start the session, let me walk you through our today's agenda. I'll start with a brief introduction to Hevo. Then Gaurav will do a detailed presentation on our today's topic. And in the end, we will do a Q&A session to address all your questions. I'll spend a minute here and give you a high-level overview of Hevo. So Hevo is a no-code data pipeline platform that connects and loads all your data that's lying across multiple source systems into a data warehouse or a data lake of your choice, such as Redshift, BigQuery, Snowflake, S3, and many others. We provide 100+ built-in integrations with different data sources, including database, data warehouses, SaaS applications, SDKs, and streaming data services, and many more. The platform supports both ETL and ELT. Hevo is currently used by customers spanning across 10 different industries and 15 different countries. For more information about the product, you can check our website, www.hevodata.com. So with this introduction, I will now jump on to the topic of today's discussion. So before Gaurav starts with his presentation, let me give you a quick introduction about him. Gaurav has over 20 years of experience in the data domain. He has worked on multiple technologies like databases, data warehouses, DWA, big data, AI, and built solutions for companies like Target, Walmart, Sprint, Yahoo, and Microsoft. He's currently working as a VP engineering at Hevo and managing the entire product development lifecycle of Hevo platform. Prior to Hevo, Gaurav has worked as a head of engineering at startups from travel and technology, fintech domain. And before that, he worked as an engineering leader at organizations like Microsoft, Yahoo, and HP. All right. So with this introduction, I will welcome Gaurav. Gaurav, over to you.
Hello, everyone. Today we'll be going into the technical details of data warehousing as a practice, as well as look at a few of the other tools which we would typically use in setting up a data analytics practice for our team. Before jumping into the details of data warehousing, I just want to kind of get the terminologies right for all of us. Databases are the kinds of systems which we use for collection of our data, typically largely operational data. It acts as a system of record for activities related to our business, something like user-related activities, customer-related activities, things like that. These systems were developed in the 70s, and the companies which kind of made the big name in those in this particular space were IBM, Oracle, Microsoft kind of players. Those systems were well designed for addressing the operational data needs. However, when it came down to analytics needs, something else was needed. And that's what we will discuss today. So data warehouses typically act as central repository for an enterprise data. It could be storing the current data as well as historical data, because typically analytics requires us to have visibility into what has been happening in the organization all this while. These act as decision support systems for businesses. The first kind of dedicated or specialized data warehouse systems were kind of developed in 80s. Teradata still exists, and it was one of the big players which came out in those days. Other database players, IBM, Microsoft, Oracle, they also added features into their products to support analytics, but they had limitations. There are, in the last 2 decades, many new different entrants came in: Netezza, Vertica, Gleedblum. Many of them are not so relevant in today's context, and we will discuss that as well. In the recent years, we have also heard another term called data lake. Data lake is basically a system where we would want to kind of store all kinds of data, which my team may have, enterprise may have. This could typically include both the raw data formats as well as the transform data. The raw data could be in the form of structured data, like the relation databases, or the semi-structured or binary data as well, like images, videos, things like that. Depending on the sensitivity towards kind of this data, we may choose to look for an on-premise solution or in the cloud. Today, we'll primarily focus on data warehouses and look at how things have changed over the years in this particular space. Before we actually get into an actual data warehouse technology itself, to understand the purpose and concept behind why data warehouses are needed and what specific role or purpose they serve. Typically, a data analytics exercise starts from the business team defining key requirements, what they would like to have measured for the particular product, enterprise, whatever the case may be. Based on those requirements, the data warehouse specs per se as to the amount of data we will be handling, the kind of queries we would be handling, things like that are identified. A specialist who's who has the knowledge of coming up with a more of a refined data model, which would be able to cater to the business needs, is something which is identified before we actually start any implementation. And the data model itself would then result in subsequent exercises around ETL, which would then help us do the mapping between the source data we have in the enterprise and how it would help us get to the data model needed for the analytics purposes. So ETL tools help us in a big way in being able to achieve that. They help us be able to pull all kinds of data from all different sources we have in the system. It also helps us be able to perform data preparation, cleansing, any kind of aggregation, things like that. Typically, ETL tools would require access to a database or a staging area where some of these operations could be performed. ETL tools would kind of, as an end result, produce dimensions and facts, which is basically the data set which maps to the data model we talked about earlier in the data warehouse. And ETL tools would then kick off the actual data load into the warehouse. Warehouse is expected to have the batch capabilities with respect to data inserts. At the same time, it must provide capabilities with respect to the query workloads we would see from the analytics point of view. Typically, the tools used would be things like MicroStrategy, Click, others. In current context, many of us are starting to look at a different way of achieving our analytics objectives. The objectives largely remain the same. However, how we approach them in implementing our technical design behind it could be different. And one of the main change there is that the ETL tool has a lesser of an emphasis in this setup. So the ETL tools in this case are more of a simplified model and just largely performing the extract and load. And the data largely represented as is in the form as it was seen in the source system is moved over to the staging area. And transformations are applied in the warehouse in form of a materialized data sets or views, as the case may be, before it is made available to the analytics layer for presentation. So as listed here, the ETL tools in this case are largely performing in this scenario an extract and load operation. So can source data, can load data. Transformations are within the warehouse and it will be performed as preparation, cleansing, as well as aggregation. And in some ways, the dimensions and facts, as it was the case with ETL, would be derived. A different kind of a transformation kind of approach has to be taken up in this case, wherein most of the transformations are achieved using SQL queries being run on the warehouse itself. Hivo does support such behavior. There are other tools like dbt, which are very popular also in the space. In this kind of design, it is very common to see that the data loads into the system are in the form of micro batches instead of a large batch, which would generally happen in case of ETL. In case of now this kind of an approach, we could actually provide a lot more real-time analytical abilities for our teams. With respect to the actual analytical capabilities, the requirements remain somewhat similar from the data warehouse point of view. Just recapping the differences between the two. So ETL, taking care of extraction, cleansing, transformation, and data inserts into the target systems. This concept, the responsibilities around data quality, consistency, schema conformance are very critical to be handled, including the fact that the data which is injected into the data warehouse finally for presentation does not necessarily need to go through any further transformation than beyond. So the analytical systems would directly source in the data as is and consume it for reporting. Such requirements, strict requirements with respect to the data being injected into the data warehouse are relaxed in case of the ELT approach. In the ELT approach, the data is being injected largely as is into the data warehouse, which results in faster load times. However, it is expected that the transformations which were otherwise being carried out by the ETL tool now have to be done in the warehouse, for which we may need extra processing capacity and capabilities in the warehouse itself. So warehouse is expected to see kind of a continuous stream of inserts as well as query workloads, whereas in case of a traditional design, that was not the case. Okay, now with that in mind, what kind of capabilities the data warehouses are expected to have? This is an important aspect for us to understand, so that then we can kind of prioritize our assessment of different warehouse options which we might be considering. So as we understood from the previous slides, ETL is one of the key element in getting a warehouse set up. Depending on the scenario, you may choose to have an ELT kind of solution as well. But it is expected that the warehouse would implicitly have such integrations available / enabled, so that these exercises could be carried out seamlessly. Same is true on the reporting as well as analytics side of things as well. So warehouses are expected to deliver on the right capabilities at a certain kind of expected throughput. Same is true on the read side. On the read side, there is expectation both from responsiveness as well as concurrency. In certain situations, there are needs from the point of view of additional query capabilities with respect to aggregates, ranking, kind of window operations, things like that. I'll not go through all the requirements here, but these are kind of comprehensive set of requirements which data warehouse typically meets. The requirements under the current context, which has started to become a lot more relevant due to the fact that many of the cloud vendors are providing data warehouse options, which are very distinct from what the traditional data warehouses used to do. So now in the current context, we are looking for flexibility. As we discussed that if we are moving to an ELT approach, wherein I'm going to see an insert and read work kind of mixed workloads throughout the day, my system should be able to handle that. And we will discuss some of those things in the options we have in the market as to how they're addressing these requirements. Scalability means in the traditional design, we were expected to kind of provide those requirements to our data warehouse vendor, and they would give us the specific kind of particular setup which would take care of those requirements. Today's enterprises are looking for more varying needs, and I would want my system to kind of scale up or down based on my needs. That's expected. Data sharing. So there are scenarios where these large data warehouses are being used as a means by which the systems, the users are wanting to share data between kind of different people within the organization. That, hey, I did this analysis. This is a data set which could help you kind of a downstream team to actually take up the next set of actions on that data. All of those things are very easily possible in new age systems. System should be simple. What we are expecting is that the ELT kind of system should have a lot lesser technical threshold for people to be able to make use of those. And that's becoming available kind of very effectively in the new design. And we would like to kind of, we expect that the system should also provide me more of a pay-per-use option versus a fixed cost option, which was the case before. So these are the kinds of things which are relevant while looking for features for comparison for a data warehouse with someone else. So what are different options? If I'm interested in looking at on-premise options, there are a few options there. Out of the list, Teradata and Exadata are probably still relevant. Vertica maybe to some extent. Netezza and Greenplum are largely in their sunset life already. On cloud, we have few very prominent options: Amazon Redshift, Google BigQuery, Snowflake, and Azure SQL Data Warehouse. We'll discuss some of these characteristics in the next few slides. So now that we understand what features we expect, now just to give you an understanding of what exactly is required or goes into making a particular data warehouse system come about. So there are kind of three distinct aspects with respect to how would you look at a typical software system or a database. So on the compute side, these systems are generally systems which can handle massively multiprocessing kind of workloads. So the systems are designed to have kind of more of clusters of CPUs working towards solving a particular kind of query or a load problem. Storage is very highly optimized for the use case, so that the reads in all possible scenarios are providing us the best of performance. So to the extent that there are kind of specialized kind of connectivity layers between the disk and the CPU to make sure that the data transfers are as efficient as they could be, even to the extent that some of these systems also provide a more of a proprietary networking layer as well, which kind of provides a lot more kind of reliability compared to the typical solutions. In a traditional kind of a solution, warehouse solution, we would end up with these limitations, that it's a proprietary hardware. It would have limited capacity, specifically kind of within the limits as to what we would have asked the vendor to support. So if it's a kind of X amount of queries, concurrent queries, and with certain query characteristics, and so those, the amount of data we would like to handle, all of those are predefined while such systems are kind of delivered to a customer. The tool support is limited to whatever the data warehouse vendor itself would provide. Now, there are not too many kind of other options. The manageability aspects are challenging because of the fact that each data warehouse vendor would have its own way of kind of managing it and requiring special capabilities on the people who are working on those systems for them to be able to operate. There is a kind of a significant time needed for onboarding, migration, upgrades, all those challenges. So these are the kinds of challenges or reasons because of which the new age systems were felt needed. So now we'll discuss the cloud data warehouse options, which are very prominent these days. So first one is Amazon Redshift, which came into prominence in 2012-2013 timeframe. Amazon basically took Postgres database and kind of changed the underneath storage layer, which is more suited for a data warehouse kind of a setup. So the way such system, this Redshift system works is that there is a concept of a leader node, and there are a bunch of these compute nodes. Each compute node has a bunch of these, what they call as node slices. Each node slice is basically the unit of compute, the basic unit of compute, which comes into kind of play every time a particular operation is initiated against the system. So the leader node would just act as a receptor. It will receive the query, compile the query, pass the kind of that execution plan of the query to the different slices, and wait for the slices to do their job. Once the job is complete, it'll collect the data, pass it back to the application. In this design, it is expected that all these components are always on. So when I provision my Redshift system, these compute nodes are dedicated for me. So that's a distinct kind of behavior of Redshift. In terms of data storage concepts, it stores the data in a columnar format, which is best suited for analytics query needs. It results in significant query boost with respect to when we are trying to do aggregations and windowing and ranking kind of queries. This data is kept in data blocks which are compressed. So in a single MB block, which it could result in thousands and millions of records getting compressed. So in this case, what I mean is that a column is being stored in a particular block, and these are those 1,000 to millions of values of that column in that one MB block. Redshift does support data partitioning and data ordering features. These are important to be considered while designing database and tables, especially for tables which will contain huge amount of data and which will generally be joined with other tables in the system. So these parameters help Redshift in being able to determine the most optimal plan for execution. Some other features which are distinct to Redshift is that it does support geospatial queries. These features were introduced late last year. Redshift has it provides capabilities with respect to being able to scale up, scale down, but that requires very little more of a cluster pause time, something in the range of 5 to 10 minutes. But those operations are available. There is an additional behavior around auto-concurrency, wherein if there were to be a scenario where during a certain period of the day, we expect to see more number of users using the system, Redshift can spin off another cluster of exact same configuration with the exact same data and start routing some of those queries to that system as well. That helps in being able to support more kind of read patterns during a certain window. It would not be beneficial if it were to be needed for a longer period. In the ways you can kind of have a Redshift cluster kind of configured for you, there are 3 different options. You can have a pure SSD based system, or you can have a magnetic disk based system. These are based on the kinds of data volumes and compute needs in terms of query response time. You could choose one of those options. Very recently, Redshift also introduced Redshift managed storage option, wherein the data is predominantly stored in S3, but at the time of query execution, Redshift intelligently would bring the required data into SSD for the duration of the query. So this provides a very balanced kind of now approach, wherein I can have a larger data set sitting in S3, and only the queryable data at any point would actually be on SD. So I get best of both in this setup. This is fairly new, so it needs to be seen how well it is designed and how well it is able to scale and meet customers' needs. From a pricing point of view, it's largely flat rate, specifically in the first 2 options. In the third option, Redshift would expect us to pay separately for the data stored in S3. Moving on to Google BigQuery. BigQuery is a system wherein we start to see a clear kind of three different layers of the system kind of getting completely separated from each other. So there is a storage layer, which is the Google Cloud Storage, the blob storage, and there is a compute engine, Dremel compute engine, and there is a Jupyter network in between these two entities. Now, what it helps us achieve is that the data is stored in GCS, and it is only picked up at the time of compute, and these compute nodes are in action for a particular customer query for only the duration of the query. These compute nodes kind of are not in any way reserved or restricted for a particular set of customer or customers. They are rather considered shared resources, but Google makes sure that it will be available for us as per our configuration with respect to what we have requested them to kind of provision for us. So from architecture point of view, the three distinct elements are the managed storage engine, the Dremel execution engine, and the Jupyter network. From storage point of view, BigQuery is also columnar storage. It also has data compression capabilities as Redshift would have it, but it does not do any compression beyond simple column compression. The block sizes are again small, but still we are able to pack a lot of data in those small blocks. It does support both the partition by as well as ordering features again, and you could use those again intelligently to make sure that you are having to scan the least amount of data when it comes to the query execution. The BigQuery design provides a very distinct feature which is not available, say in case of Redshift, is time travel. Time travel is a feature wherein BigQuery is able to track each and every change happening to a table in the system atomically. So if I were to do an insert operation, and so it is able to track as to how many records / blocks in the system got changed, and if there were to be any need of it be required to be reverted, there are ways to be able to do that. So in this case, this acts as a way to version each and every change in the system and atomically be able to track it as to however we want to kind of have a look at it. So some of these things result in the fact that we may not necessarily have to always worry about or think of taking data backups, because you are able to go back in time and look for what was the state of the system at a previous time in the past. The BigQuery provides two distinct features. One is a BigQuery ML, which helps us do some of the machine learning kind of exercises with respect to model training and model execution in SQL format itself. Very recently, BigQuery also introduced a BI engine, which provides additional query caching capabilities, which helps us improvise analytical kind of query kind of workloads in the system. The way we would configure my BigQuery account would be around how many slots I am interested in kind of having allocated for my use case. Those slots are the ones which actually come into existence and perform actual query operations when a query is basically sent to BigQuery for execution. So what would happen is that the data is pulled from the storage layer using these workers. Workers are the slots in this case. The nice feature with BigQuery is that it can create this hierarchical execution model, and in which case the data shuffling, whatever is happening, is happening between these different worker layers, and ultimately the results are then passed back by the master back to the client. From a pricing point of view, BigQuery provides a pay per query option, wherein you are only paying for the specific query execution and nothing more. It does provide a flat rate option, which was introduced recently. We'll discuss a little more about it a little later. There's another option we will discuss today. It's called Snowflake. This is yet another very interesting and powerful kind of offering. Snowflake came into existence in 2015. The way they have designed the system is that somewhat similar to Google BigQuery, we do have a storage layer holding all the data. So that particular behavior is very similar. But when it comes to compute, we have options of being able to kind of set up multiple different clusters, query clusters. So what happens in case of Snowflake is that it intelligently understands when a user query, whether it's an insert or a operation has been initiated, it will basically start the cluster automatically and have the cluster execute the operation, make the change, whether it's a change or if it's a select, it will do that. And automatically the cluster will be shut off after the use is over. So in which case the compute layer becomes flexible for us to be able to work with. And we could have multiple different virtual warehouses created to work with the exact same data. So in which case I can have a particular virtual warehouse only for insert purposes, another one for purely for query purposes. There is a services layer at the top which takes care of all the metadata with respect to the tables, with respect to security, everything in the system. So as we discussed, it has virtual warehouse, blob storage, and common services. From data storage point of view, it looks again somewhat similar to the other options we discussed. It has columnar storage. It does provide compression. It does pack the data in a compressed form in block storage. It provides cluster by operation. It does not provide ordering. It claims that those the way the system is designed, ordering of data would never be necessary, and it can still be able to perform as efficiently as any other data warehouse. The time travel option we discussed with respect to Google BigQuery is applicable in case of Snowflake as well. And same way we can kind of atomically check each and every change which happens in the system. There's another cool feature in Snowflake, they call it zero copy clone. That is wherein we can create a clone of a table using a single command, and that clone actually does not occupy any physical space in the beginning. If you were to perform any operations against this clone, that's when a new blobs will be created, and those will be distinct from the original table itself. So in which case, one could create copies of the data for, say, testing purposes, and kind of be able to safely work with it without having to worry about the cost implications in any way, or even being able to kind of harm the data in any way. From cluster configuration point of view, we get to choose what kind of virtual warehouse we would like to set up. We could have anywhere from a single CPU to a 128 CPU option. From a pricing point of view, you would be charged based on storage cost as well as the warehouse uptime cost. So that way, it is you're paying for the resources you use. The only difference with respect to BigQuery is that in case of BigQuery, the compute layer is completely kind of is away from us. We don't get to see it. We don't get to kind of own it, or we don't get to even configure it beyond the slots. In case of Snowflake, we have that option. The other options we could look at could be things like Azure SQL Data Warehouse, which is somewhat similar to Redshift with the managed storage option. For the fact that Azure provides a few other tools like Power BI and analytical engine, you could look at kind of those as combined offering for your for setting up your analytics system. In certain cases, when we are just starting to kind of work on our analytical practice, we could start off small by using a traditional database as well. These days, those databases do have the required query capabilities, so you could work with them as well. Say if you're working within the range of few tens of GBs of data, you do need to keep in mind that if you were to go beyond those needs, you would have to plan for a proper data warehouse at a future time. Now, having understood about the cloud warehouse options, now why would you would want to consider a cloud data warehouse option kind of more often these days than an on-premise option. One is that for the reason that we discuss about the pros and cons of ETL versus ELT, and the fact that with respect to the knowledge of these systems in the larger technical community being a lot more common than it was the case with traditional warehouse, your onboarding time is far shortened. The cost aspects are something which are very promising with respect to pay-per-use model. With respect to flexibility, we are able to scale up, scale down on need basis. That was not possible so easily in the traditional warehouses. The maintenance was kind of additional area which was of concern because it required downtime as well as it required special resources. With respect to how Forrester has ranked different cloud options, AWS, Redshift, Snowflake, Google, they are all leaders in the space. Microsoft kind of jumped into it in the last couple of years, but it's catching up fast. Okay, quickly checking on the feature comparison between some of these data warehouses. The things to notice are that data types support within Redshift is somewhat limited. If in case you have needs around being able to store JSON data kind of things, then you should just look for ways in which either you can flatten it out or look for ways whether you can use BigQuery or a Snowflake option. With respect to storage versus compute separation, Snowflake and BigQuery truly provide it from the ground up. Whereas in case of Redshift, only if you're using RMS option, you have that. The cost per TB is somewhat similar. Redshift has a bit of a limitation on upper end of the storage, what they can support. Currently, it's 8 petabyte. That should still be sufficient for kind of the typical largest workload we would come across. But one should be aware if that were to be a concern at some point, then that's something you may want to resolve before moving ahead. With respect to the fact that the cluster setup in case of Redshift happens up in advance, your compute resources are dedicated for you. You do need to kind of think through your options on the different query capabilities you would want to have the system support. And based on that, you would want to have the system configured for you. It looks easy to set it up after that, but at least that question needs to be answered before we can start. On the maintenance front, Redshift traditionally, because of the fact that it came from the traditional warehouse kind of a environment, it did have some challenges on the maintenance. Amazon is trying hard to kind of make it most of those operations automated. But yes, once in a while, we have heard customers kind of raise concerns around this. With respect to tools, Redshift, for the fact that it's built on top of Postgres, many of the tools which work with Postgres do work with Redshift as well. So it becomes easy to kind of work with it. With respect to BigQuery and Snowflake, if you're using typical solutions, even if it were to be with respect to connecting via scripts, it's perfectly fine. But if you have very kind of unique needs for your own use cases, then you should definitely double check whether that's supported for BigQuery and Snowflake. Workload management is an area of concern slash kind of setup for Redshift. It does provide an automated mechanism, whereas you can let the system decide for you. But for a kind of a scenario where customer is definitely looking for a finer control over it, then they need to understand how workload management works and plan accordingly. With respect to streaming, Redshift and BigQuery have a slight upper hand. for the fact that Snowflake has this Snowpipe option, which is currently available only on AWS and Azure, but it's not available on GCP. So I think I probably missed highlighting one part related to Snowflake, is that Snowflake is an offering which can be made to run on the three leading clouds. So it can be made to run on the AWS, Google, GCP, or Microsoft Azure. So while we are setting up, we are provided option to choose one of those systems where we would like our warehouse to be hosted. So now that we have understood the different requirements, the capabilities, now how would we go about kind of picking one data warehouse for our own specific use case and need? If we have a particular vendor preference that we are already using AWS for certain kind of functions in the system, in our setup, and we would prefer to kind of continue to work with AWS, perfectly fine. You could choose to use Redshift. Likewise, the offerings from Microsoft and Google are equally powerful. When it comes to objective, you could apply a check on whether you are only in need of a database/data warehouse kind of setup, or at some point you may also want to have a data lake kind of a setup. Because Snowflake by itself doesn't provide its own storage and other kind of query capabilities besides its own engine. So if you have things like, if you want to use a Hadoop or a Spark kind of engine to kind of work on your data, then you may have to look at data lake kind of a setup on one of these clouds. And if you are only considering a data warehouse as an option, then obviously Snowflake is a very prominent offering here. From a manageability point of view, Redshift and Azure SQL Data Warehouse have a somewhat of a similar design, because of which they do present similar manageability challenges for teams who are not so well versed with managing such systems. In case of BigQuery and Snowflake, the manageability aspect is far streamlined. On the tools front, Redshift and Azure Data Warehouse have a upper hand because of the fact that the underlying kind of technologies they are using have been in existence for a long time. Postgres in case of Redshift, and SQL Server in case of Microsoft. When it comes to query patterns, if you have a very well-defined setup for your queries, for your insert workloads, then you can get the best performance out of Redshift and Azure Data Warehouse. For the fact that then you can use them to their almost 80–90% kind of capacity, and you would be kind of better off with respect to price performance. However, if your setup is evolving in nature, that you are not fully sure of what all kinds of analytics you would be keen on doing, what kind of workflows you expect to see in the system, then the models provided by Snowflake and BigQuery are better suited for it. When it comes to kind of a additional dimension around normalized data versus denormalized data, in principle, all the warehouses recommend that we use denormalized data because that helps us avoid joins at runtime. And because of the fact that these systems use columnar storage, we are able to kind of pack a lot of data in a lot less space. At the same time, the aspects around number of columns being in the system is not necessarily a significant overhead in any way. So that's a general practice recommended by all the vendors. However, for the fact that in case of Redshift and Azure, your query capacity is pre-allocated, is guaranteed for you. So you would never kind of reach in any way any kind of thresholds which you would otherwise like to put for query execution. Whereas in case of Snowflake and BigQuery kind of systems, like BigQuery specifically, that for the reason that there is actually no limitations other than the number of slots. And if I have kind of sufficient number of slots, it can kind of run the most of complex queries in few seconds, that works fine, but it comes at a cost. It results in much kind of significant cost than we would have thought of or provisioned for. That ends up kind of hitting us badly towards the end of the month. So with respect to being able to use one versus another, one needs to be aware of these aspects very clearly to be able to avoid any kind of unforeseen situations with respect to cost. If you have specific requirements around machine learning capabilities, currently it looks like BigQuery is moving a little faster than other players. So you can definitely look at the options provided by BigQuery for machine learning today and what's coming up in future. And if that were to be the case that it meets your requirements, you may choose BigQuery. If you are light on those requirements, these systems do also support things like linear regression, logistic regression, some clustering, some few features around that they also support. So this is the last slide. Thanks a lot for listening to me. Parag, do we have questions?
Yes. Okay. So thank you, Gaurav, for this insightful presentation. Now it's time for Q&A. We have some questions coming up. Let me read one by one. So first question is, in ETL, as the data cleansing and transformation are done in the data warehouse itself, then won't it impact the performance?
Let's go back to slides. So yes, it will. It can, if it were to be the case that my warehouse had limitations on the compute side. For the fact that, say, in case of Snowflake, I can choose to have a cluster only for ingestion and a separate cluster for query. So my ingestion workflow will not have impact on the query. So my queries could continue to run while my ingestions are happening in parallel, but that's in a completely independent compute setup. There is a possibility that if there were to be the case that the table which is being queried is the same to a table being inserted into, in those scenarios is still it, because of the fact that it does not follow a typical asset design as we would have for a RDBMS kind of setup, it does not necessarily result in any kind of contention in the system for the fact that the operations are performed atomically. So the if and when the operation completes is the time when the change is seen by the query, the select query. Till then, it's not visible. The same is true for Snowflake, other systems like BigQuery as well. In case of Redshift, it has to be planned and accordingly. So while the workloads could be planned, but as I mentioned earlier, that from a workflow setup point of view, there is Redshift provides a workflow management feature of its own, auto workflow management, as well as a manual workflow kind of balancing could be done where we can say 5% of the capacity is reserved for insert or the load purposes, and rest of the 95% is available for query.
Cool. Okay, now there is a second question that is coming up, which is, what is the performance difference on performing analytics on database versus data warehouse like Snowflake?
So I would say that database is a poor man's solution towards achieving analytics. Not that they lack in features, they do have their own kind of limitations beyond which they would not be able to scale. So if you are, as I said earlier, that if you are within maximum of few tens of gigabytes of data, you would just be fine with databases as well. But typically any team setup, any analytics projects run sort of kind of that much of data space in few months, maybe few years, depending on your use case. But yeah, that it's a short-lived approach. It doesn't work for a long duration.
Sure. So we'll take one last question and we'll move on with the next slides. So the next question is, if I have figured out a data warehousing provider to go ahead with, then what should be my next logical steps in setting up the analytics and managing the data in future?
Sure. So with respect to kind of having figured out the data warehouse is I would say 10% of the the kind of solution to this problem. Now, with respect to what your business objectives are around kind of specific matrices, specific reporting, which you want to have the system deliver for you, somebody needs to kind of take the responsibility of actually being able to define a data model which will help you get there. No system today is simple enough that we have 2 tables, 3 tables that you just make join against those and you have your end reporting requirements met. You would typically be actually merging data from multiple different systems before being able to kind of arrive at a data set needed for your analytics needs. And then comes the work around transformations, and finally the reporting, which itself has to be a task around identifying which tool will meet my needs, whether it's Tableau, Power BI, Click, MicroStrategy, you name it. So there are various different options. So all of those aspects are equally important in us being able to achieve our analytics objectives.
Sure. Okay. Thank you, Gaurav, for this, for these answers. Now let me stop sharing your screen. I'll just put up my screen.
Sure.
All right. So we are conducting our next webinar on 30th of July, and the topic is build versus buy data pipeline approach. We will send you the webinar details over an email, and you can also check our website and go register there. So I would like to thank all the attendees for joining us today, and special thanks to Gaurav for sharing the knowledge and experience with all of us. If you are interested in knowing more about Hevo or want to schedule a demo with our product expert, then please visit our website www.hevodata.com. You can also sign up for a free trial there. If you have any questions or feedback about this webinar, then please write to me on Parag, P-A-R-A-G @hevodata.com. See you for our next webinar. Till then, take care and stay safe.